Hi, so in this video, we're going to talk about independent events. So two events, E and F, are going to be called independent if the probability of them is not affected by knowing that the other one happened. So in terms of a conditional probability, we're going to write it like E and F are independent if the probability of E given F is equal to the probability of E. So knowing that F happened is not going to change the probability of E. Or the other way around, it doesn't matter. It's symmetrical. The probability of F given E is the same as the probability of F given E. So if the events are not independent, of course, we're going to call them dependent. And the examples in the past videos, the examples were dependent. So that would be that knowing that one of the events happened does influence the probability of E. So the probability of E given F is not the same as the probability of E. Let's go over some simple examples to have this idea around our head. So let E be the event. I select a person at random from the street, and the event E is that the person has a master's degree or higher, and the event F is the person selected earns more than $100,000 a year. So the question is, are these two events independent? So does knowing that one of them happened, would it change the probability of the other one happened? So there's a probability that you just meet a person in the street or you're surveying, and that person has a master's degree. There's another probability that that person that you selected earns $100,000 per year or more. So knowing that one of those things is true, does it change the probability of the other one happening? We're not saying does it imply, or is it the only way that it would happen? We're just saying, would it change the probability, right? And the answer is yes. These events are not independent because the probabilities will be changing, right? So knowing that the person has a master's degree will increase the chance that that person earns $100,000 a year or more. My second example is just written very simple. Pretend you select a car at random from I-5. You're on a bridge, or you see a camera or something, and you follow a car going over 85 miles per hour. And the other event is, this is not the way it's written. It's written, you select the car at random, then the event E is the car you selected is going 85 miles per hour. The event F is the car will be involved in a car accident. So knowing that it was going 85 miles per hour, then it will increase the probability of being in a car accident. So these events are not independent. Okay. So let's do some examples here. Here it says a die is rolled twice. What is the probability that you get a 3 on the first throw and a 3 on the second throw? So I'm going to paste. I think I have it here pasted. Yeah, this is how I have the multiplication rule for conditional probability. But what I'm asked here, so the event E is going to be I landed a 3 on the first throw. The event F is it landed on the 3 on the second throw. So what I'm asked to find is this one. What I'm asked to find is the probability of E and F, right? And what this is the right side on the numerator. So I'm going to solve for that and say, well, if I want to find that, why don't I multiply by this denominator? And multiplying has the effect of showing up on the other side, right? So when you multiply, it would cancel on that side and show up on the other side, multiplying. So now I have this nice formula that says the probability of E and F, which is what I'm asked to find, is equal to the probability of E times the probability of F given E. So this is called the multiplication rule. Now, what I want to see is that what is the probability that I got a 3 on the first throw of rolling a die? Well, this is clearly 1/6, right? 1 over 6, the probability that I get a one number out of 6, and all of them are equally likely. Now, the probability of the second part is the probability of the second throw being a 3, knowing that the first throw is a 3. But if you think about it, knowing that the first throw is a 3 didn't affect that what's going to be the probability in the second throw, right? So if I roll the 3 in the first throw, if I roll a die, and you don't know what happened, and I ask you, what's probably like when I get a 3 in the second throw, you're going to say 1/6. And if I tell you, oh no, but the first throw was a 3 already, the probability is still 1/6. Okay, it's not different. So knowing that the first throw was a 3 does not affect the probability of the second throw. So it's again 1/6. Okay, so that's the answer here. Is just 1/6 times 1/6, so it's 1/36. Okay, so I'm going to copy it in this version of it, because that's the way I'm going to use it for the next one. Now a die is rolled and a coin is flipped. What is the probability that you get a 3 on the die and tails on the coin? So it's going to be exactly the same formula, right? E is going to be the die is rolled. E is I get a 3 on the die, and F is I get tails on the coin. So, of course, the probability of getting a 3 on the die is again 1/6. The probability of getting tails on the coin, knowing that I got a 3 on the die, it doesn't matter. It's still going to be 1/2, right? Whatever happened on the die doesn't affect what happens. It's going to happen with the coin. So I'm just multiplying, right? It's going to be 1/12. So the important thing here is that I didn't write in the other one is that this is really the same as the probability of F, right? So the probability of E and F turned out to be the probability of E times the probability of F. And that's happening because the events are independent, right? Because knowing that E happened does not change the probability of F. So this is what is called the multiplication rule for independent events. So if you have events who are independent, and you want to know what's the probability of one of them happening and the other one happening, then you just multiply the probabilities. If you know that the events are independent. Now, sometimes we're assuming the events are independent when it's hard to have that assumption for real. I'll see in examples, but this is how it works. Now, in terms of Venn diagrams, I showed you a few examples ago that when you have sets and you're making the picture in Venn diagrams, that's the intersection. So I didn't use the symbol, but this is the symbol for the intersection. Okay, so it's like a cap, an upside down U. So if the events are independent, this turns out to be this. So this is some examples. So the probability of a knee surgery is successful is 85%. Pretend this is true for some special knee surgery. On a particular day, a team of surgeons are going to perform 3 knee surgeries, 3 of these knee surgeries. So what's the probability that all 3 are successful? So what I want to say here is that it's we're going to assume that the second surgery being successful is independent from the first one being or not, and the third one being is independent of what happened in the first 2. So when you do things in a row, one after the other, you can think of it like like I did in the past example. So it's going to be 0.85 for the first surgery, 0.85 again, and 0.85 for the third one. Yeah, so this is going to be 0.85 to the third power. You can put it like that, 0.85, 0.85. Okay, and of course you type that in a calculator and you get a nice approximation. So let me bring my decimals calculator here. So I'm going to go 0.85 to the power of 3. So it's 6141. Okay. So now the second example I'm going to ask here is find a probability that none of the 3 surgeries are successful. So if it wasn't successful, that means that it was a failure, and that's going to be 15%, right? So it's a 15% or 0.15 chance of being non-successful, and all 3 is going to be the same logic. It's going to be that 0.15 to the third power, right? Because 0.15 for the first one being non-successful, if we assume that the second one is independent from the first one, and so on. So it's going to be 0.15 to the 3. So I'm going to put that here. So it's 0.15 to the third power. So 003375. I'm going to be consistent and use 4 decimals. 0034. Okay. Now, my last question, I'm going to leave this open there, says find a probability that at least one of them is successful. Now, this is a little bit harder because most of the times when students are seeing this for the first time, they say, "Oh, that means one success. One is 0.15, and the other two are 0.85." Well, that is not at least one. That's exactly one, right? So what the question is asking is, it's either one was successful, or two were successful, or all three were successful. That's what this problem is saying. And even the first one, when I said one successful and two failures, it's not the same if you have three people and one of them got successful. If they tell me one of them were successful and the other two were not, I want to know which is the one who was successful, right? It's different. There are two different outcomes of the three, of being only one successful. But anyway, that's not the best way to approach it. The best way is use the complement. So if this didn't happen, if it's not true that at least one was successful, let me paste what I had here. So this was the answer for the last question. That was the answer for none of them were successful. Okay, so all three were failures. So the complement of all three failures is exactly what I'm asked on the third one, right? So I'm going to write here something like the probability of at least one success is equal to 1 minus the probability of all failures. I hope you see that, right? If it didn't happen that all three were non-successful, it means exactly what the third question is asking, right? So they're complementary, and that's something we saw in the beginning of probability. So it's going to be 1 minus my last answer. So it's going to be 1 minus, oops, not 2, 1 minus 0.003. Oh, I didn't want that. Sorry. Let's try it again. Well, I can do that in my head, but it's not what I want. 0034. There you go. So 9966. Okay, so this is how we use the complement to find these probabilities. So I hope that's clear. I have one more example I'm going to squeeze into this video to not make another one. And it's the same spirit. It says, suppose there is a 30% chance of rain in each of the next 3 days. And I'm going to assume that they're independent. Okay? The fact that it rained on one day does not affect what's going to happen on the second day and so on, which is probably not true, but let's assume that that's the case for this example. So what's the probability that it will rain in at least one of the next 3 days? So here's again, it's better to find the complement. Okay, it says at least one, so the probability that it rains at least one day is equal to 1 minus the probability that it doesn't rain in any of the 3 days, right? That it does not rain on any of the 3 days. Not rain any day. So I hope you see that. Rains at least one day is the complement of it didn't rain at all, right? So it's easier to find the probability that it didn't rain at all. If it's 30% chance of rain each of the days, it's 70% chance that it doesn't rain on any of the days, right? Any singular day. So it's going to be 1 minus 0.7, 0.7, and 0.7. Right. So then it's going to be, let me go back to my calculator. It would be 1 minus 0.7 to the third power. Okay, 65.7. Okay, so I hope you see how it's useful to use the complements instead of finding them directly. Finding them directly would be more complicated, to do it correctly, we would have to do with the probability that at least one day would be, we had to add the probability that it rained on exactly one day, right? And then there's which of the days, it could have been the first, second, or the third. Then we have to find the probability that it rained exactly on 2 days, and add it, and then the probability that you have on all 3 days. But this is a lot simpler. This is the way to do it.